Hello everyone, Victor is here, and in this video we are going to continue talking about the Lewis structures and constitutional isomers. So let's look at this molecule. We have C4H10O. Now, as we have discussed in the last video, the first step to build the possible structures for this molecule and this molecular formula is to start with the building blocks. In this particular case, I have 4 carbon building blocks, so I'm going to draw those. Then we have 10 hydrogen building blocks, and we have 1 oxygen building block, so I'm going to show that, and I will show the electron pairs on the oxygen right away as well. And one question that a lot of my students ask me is, how do we know how many structures we are going to make? How many constitutional isomers are possible for a given molecular formula? Well, we don't really know that, and there is no really any good way to calculate that either. So to make sure that we do indeed draw all possible structures, we must have some sort of strategy or an algorithm, if you like. And I suggest starting with a straight chain and then slowly vary your molecule from there. So for instance, I'm going to start with just drawing 4 carbons in a chain like that, and then I will add oxygen to the end of this chain. Then I can draw straight chain with 4 carbons again, and now I will add oxygen to the second carbon. Now, once I have added my missing hydrogens and electron pairs, I have molecules 1 and 2 over here. I have my first 2 constitutional isomers. So at this point, I'm going to move one of my carbons to the middle of the chain. So if I have a chain where I have now 3 carbons and 1 is sitting in the middle of that, I can get oxygen sitting on this side. Or another possibility is going to be if I have oxygen in the middle of the molecule like that. Again, adding all the missing hydrogens and electron pairs gives me isomer number 3 and the isomer number 4. Now I can start inserting oxygen in between my carbons and see what that gives me. In this case, I can get one structure in which I have 2 carbons, oxygen, and 2 more carbons like this. Or I can have a structure where I have 1 carbon, oxygen, and then chain of 3 more carbons. Or one other possibility will be if I have a 3 carbon chain, then oxygen, which is then connected to carbon as well. And since I'm kind of running out of space here, I'm going to squeeze those hydrogens all together, but overall that gives me my isomer 5, 6, and 7. And at this point, all these structures, as I've mentioned before, they're called constitutional isomers, or sometimes you can hear a term structural isomers, because they all have different connectivity between the atoms in the molecule. And here is something very important though. If I take one of these molecules and redraw it in a few different ways, let's say like that, what I have here is the same molecule but drawn in different way. So these all structures, these 4 structures that I have on the screen right now, they all represent exactly the same molecule. So here is the deal. Molecules don't really care how you draw them. They just, well, exist. So if you draw a molecule differently on paper, that doesn't really change the molecule itself. Single bond and carbon chains can freely rotate in space. Thus, it's more important to focus on the order in which atoms are connected to each other rather than how exactly the chain is twisted in space. Like for instance, in this particular example, I have a chain of 4 carbons over here, and at carbon number 2 I have the oxygen. The example on the right, I again have 4 carbon chain, and if I number it from the right side, 1, 2, at the second carbon I have the OH group. The one in the bottom left, I have a 4 carbon chain, and at the carbon number 2 I have an OH group. And finally, the bottom right, again I have 1, 2, 3, 4 carbons in a chain, and the OH is connected to my carbon number 2. So the important thing here is the order in which they are connected to each other rather than simply how they look in space or how we draw them on paper, because as I've mentioned, molecules don't care how we draw them. Alright, Let's look at another example. So now I have C3H6Cl2. Here, the building blocks are going to be 3 carbon atoms, so I'm going to draw those out. I have 6 hydrogens, and I have 2 chlorines, so I will show those with all electron pairs around them as well. Since chlorine is limited to only making one bond, because we have possibility just for one bond and the electron pairs are not going to be participating in bonding, we are going to be using that essentially at the end of our molecule. We will not be able to insert our chlorine in the middle of the molecule. So this way, I'm just limited to simple 3 carbon chains without any chlorines in the middle of it. So the first one will be something like carbon, carbon, carbon. Then let's say I'm going to add my chlorines to the end carbon. Then I can have 3 carbon chain, but now I'm going to have 1 chlorine in the middle, 1 chlorine to the right. I can also have a 3 carbon chain where I have chlorines connected to the end carbons, and finally I can have one last form, or one last constitutional isomer, I should say, where my chlorines are both sitting on the middle carbon like that. So by adding my missing hydrogens and the electron pairs, I'm going to end up with 1, 2, 3, and 4 possible constitutional isomers for this particular molecular formula. Now, on your paper, when you're doing this example, it is quite possible that you might have ended up drawing it in slightly differently. However, pay attention to how exactly the carbons and chlorines are connected, and for as long as you don't have any repeats, you should also have just 4 structures like what I have here. Now, how do I know if my molecule going to have a double or maybe even a triple bond or maybe even a ring? Well, I can either brute force it and figure it out while building the structure itself, or I can use a nifty little trick called Hydrogen Deficiency Index or degree of unsaturation. We can easily calculate the HDI using the following formula. We're going to take twice the number of carbons plus 2 minus any hydrogens that we have in the molecule minus any halogens plus nitrogens if we have any. We're going to ignore oxygens and sulfurs, divide that by 2, and we are going to get some sort of a number. So that is going to be our hydrogen deficiency index. Each degree, each number that we get out of this formula means that you have either a double bond or a cycle. So a triple bond, for instance, is going to take 2 degrees. And that's important because this gives you the types of features that you might potentially see in your molecule. So if my HDI equals 1, then I'm going to expect either a double bond or I'm going to expect a cycle. If my HDI going to be 2, then I can expect 2 double bonds, I can expect a triple bond, or I can expect a double bond and a ring, or I can expect 2 rings in my structure. Likewise, if let's say my HDI going to be equal, say 3, well, in this case we have even more possibilities, because then we can expect either 3 double bonds, or we can expect a triple bond and a double bond, or we can expect a triple bond and a ring, or we can expect 2 double bonds and a ring, or we can expect double bond and 2 rings, or I'm running out of space here, we can expect potentially 3 rings in our molecule. As you can see, the variability of your possibilities grows exponentially with each degree, but this is a useful piece of information when we are trying to come up with the constitutional isomers, as this tells us right away what type of structural features we should expect in our molecule when assembling the initial skeleton for the structure. So let's look at the following molecule, for instance. I have C3H6O. If I first calculate my hydrogen deficiency index here, HDI, what I'm going to get is twice the number of carbons, which is 3, plus 2, minus, I have 6 hydrogens here, I don't really have anything else, then divided by 2, I'm going to get 1. So I have 1 degree of unsaturation, which means that I should expect to see either a double bond in this molecule, or I'm going to see a ring, or a cycle if you want to call it this way. So I'm going to incorporate those features into my skeleton as I'm building it right away. So let's start with a straight chain of carbons and we'll add oxygen to it. So I have carbon, 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 oxygen. There are 3 potential places where I can put a double bond here. One is going to be between my carbon and oxygen, or I can have a situation where I'm going to have a double bond in the middle like that, or I can have a situation where I'm going to add my double bond on the left side. And by adding hydrogens and the missing electron pairs to my molecule, I have my first 3 constitutional isomers. Now I have to move my oxygen somewhere else. Let's say I'm going to move my oxygen to the middle carbon, so that gives me a skeleton that kind of looks like that. I have carbon, 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 and now my oxygen is sitting over here in the middle. Now, in this case, there are 2 possible places where I can add my double bond. I can put it over here, or I can put my double bond in between carbons. Let's say I'll do it on the left side like that. And like before, I can finish off my molecule by drawing the missing hydrogens and the electron pair to have the complete Lewis structure. That gives me my constitutional isomers 4 and 5. So the final acyclic structure that I can get here is going to be the one where I insert my oxygen between carbons. So if I draw carbon, carbon, then oxygen, then another carbon, then the only valid placement for the double bond in this case is going to be between my carbons like that, which, by adding the missing hydrogens and electron pairs, gives me my last acyclic constitutional isomer. I'm going to call it molecule number 6. At this point, when I've exhausted all acyclic, or open chain in other words, possibilities, I can move on to the cyclic versions. And probably the most obvious and one of the most straightforward structures that I can come up with here is going to be where all of my core atoms make up the 4-membered ring. So I'm going to end up with the molecule with a carbon, oxygen, carbon, and the last carbon, making a 4-member ring as such. And to finish this molecule, I just need to add my hydrogens along with the electron pairs on the oxygen to make a full Lewis structure for my 4-membered ring with an oxygen, which by the way called oxetane. Then I can also make a couple of 3-membered rings. One is going to be where I have 3 carbons in a ring and oxygen is going to be hanging from one of those rings. And I can have another version where I have carbons and an oxygen in the ring, which means that my 3rd carbon will have to be hanging off the ring like that. So in this case, I'm going to end up with my last 2 constitutional isomers, molecules number 8 and 9, that incorporate those 3-membered rings. How did you do? Let me know in the comments below. So now you're ready to tackle any problem that requires you to draw all possible constitutional isomers for a given molecular formula. Keep in mind that the number of constitutional isomers increases exponentially with each additional atom in the molecule and each degree of unsaturation as well. I don't really expect you'll see a question like that on the test, although it is possible, and I have seen those before, but it is certainly a fair game for a homework or any kind of test that you are going to take home, or maybe a lab work or something of that sort. So, as you can see, drawing constitutional isomers might be a bit tedious, but not really intrinsically difficult. It does require good attention to detail though, which is a crucial skill that you are going to need to succeed in organic chemistry anyways, so now might be a good time to develop it anyways. So, are you ready to work through more practice questions? Then check out links below for the Constitutional Isomers workbook. Let me know what questions you have in the comments below, and I'll see you next time.